In my previous video, I introduced you to one of the timers in the microcontroller, timer counter 0, and I just gave you a brief overview and showed you how to set it up to give a regular interrupt. In this case it was every 10 milliseconds, and I talked about a couple of the registers that are involved with the timer counter. The main counting register that's driven by some oscillator, some frequency, and then these two output compare registers, which when set up appropriately will also toggle an I/O pin. Each of them will toggle an I/O pin. I'm going to go into a little more detail and show you how to use the timer counter in the PWM mode. Now there's actually, I've got written down here 4 modes of operation, but there's actually 6 modes of operation, and the two PWM, these two, phase correct PWM and fast PWM, have 2 additional modes that modify how they actually operate. But they function pretty much the same way. There's just something that'll change, but I'll explain that in a minute. But let's go through the different modes here in a little more detail. So the simplest mode is the normal mode. And if we were to draw a little graph here of the timer counter registers count in time here, so as it increments, it just goes up this ramp, it reaches a maximum and it rolls over and starts over at 0 again and just keeps ramping up and down like that. And that's generally how you run the timer, or you can do it in a different mode here where it goes up and down, but I'll talk about that in a minute. So in the normal mode, the timer counter simply increments to the maximum, which in this case is 255, which is all 8 bits are 1, and then it just, on the next count, it rolls over back to 0 and starts again. And there isn't very much you can do with it. An interrupt flag would be set every time this thing rolls over to 0. You can also use one of the or both of the output compare registers, and when the timer counter reaches one of the values of the output compare register, it'll generate a different interrupt. And that's assuming, of course, you've got interrupt set up in the microcontroller. It does set a bit every time, which you can check under software. You can poll it and just keep monitoring it, and when it gets set, you know that it's either rolled over to 0 or one of the output compare registers is matched. So that's the normal mode. You can actually have the output compare register drive one of the I/O pins if you wish, but it doesn't really produce any kind of a useful signal, so it's not recommended that you do that. Now I'm going to skip the phase correct PWM mode in a moment, and then we'll look at it in a moment here. The next mode is the one that I showed you in the previous video, which is clear timer on compare match. So what you do in this case, or what happens in this case, the timer still goes up, increments like this, but when it hits the value of one of the output compare registers, it immediately gets cleared to 0, and then it starts up again. And so that way you can set a fairly accurate time from 0 to where it matches, and then it generates an interrupt again. And that's the method I showed you in the previous video, and that's how we got the 10 millisecond interrupt. And so let's look at the fast PWM mode first, which is this one here. Now again, the timer counter register is incremented based on the frequency that you give it from FCPU, and it increments all the way up to the maximum, and then drops, rolls over and starts at 0 again, and does exactly like this again. Now you have the output compare register programmed with a certain value, and then you have to set a couple of other bits in one of the control registers in order to turn on the I/O pin in order to get it toggled. And you also have to set up that I/O pin as an output pin. When you set up the PWM modes in the timer counter here, it does not automatically set the I/O pin to an output. So the way this PWM works is that the output pin is cleared or set to 0 when the timer counter reaches 0, or sorry, it gets set to 1 when the timer counter starts counting up, and then when the output compare register matches the timer counter, the output pin gets cleared to 0, and it'll stay 0 until the timer counter reaches its maximum or goes back to 0. I'm not sure exactly what triggers that point, but it's the same, pretty much the same point. and then the output pin will go low again, and then the process repeats. And if you change the value in the output compare register, like I've shown here, you can change the length of the time that this I/O pin is high. And there's a couple of modes that you can set the I/O pin to. There's 4 different modes, and 2 of them are what I just described here. But the other mode is to invert this pin, so that it would be high at this point and low at this point, and high here, low here, etc. It would just be the exact opposite phase of this one. I just drew it like this for simplicity, because this is how most PWM is described, is the high time versus the low time. And the more on you have something, say the brighter the LED that you're driving would be. So that's the fast PWM, and there you can have 2 different outputs from this mode here, because you've got the 2 output compare registers, and they can be independently programmed to different values, so you can have 2 separate independent PWMs. And the only thing that's common between the 2 PWM is this period here, which is between the time that the timer counter register rolls over. And you notice that the period is the same length all the way along. So that's the fast PWM. And then the other PWM mode is the phase correct PWM mode. And in this case, the timer counter register will increment from 0 till it reaches the maximum. In the manual, when you read this, you will read the term top, and that's the maximum count that the timer counter register reaches is called top. And so in this case, the timer counter will increment to top, which in this case is 255, or the maximum count of 8 bits, and then it turns around and starts to down count down to 0, and then it increments back up and down. So you get this more sawtooth wave. And then again, you program your output compare register. And so when there's a match on the rising, when the timer counter is incrementing, the output pin goes low, and then it stays low until the counter is decrementing and it reaches the same value of the output compare register again, and this time it sets the pin high. And so again, you can change the PWM by varying the value in that register, as I've shown here. You can see where it changes the state of the output pin. And so when you vary the PWM in this mode, what you're going to get is these pulses here getting wider or narrower. Again, the period is the same, so your on time per period is going to be this determining the duty cycle of the PWM. In the fast PWM mode here, what you're going to see is always a rising edge here, and then the top here just moving back and forth as you change the value in the PWM or in the output compare register. So what I'll do is I'll program my microcontroller here to do either of these 2. I'll show you both, and then I'll put them up on an oscilloscope where you can actually see how the PWM signals change as the PWM is changed. So what I forgot to mention here before we go on and look at those control registers, the 2 additional modes of the fast PWM and the phase correct PWM. And the other 2 modes, the only difference is they change the value here of the top. And in the phased correct PWM mode, you use the output compare register A, and that determines how far up the timer counter register goes before it starts to count down again. And in this case, you can only get 1 channel of PWM because you're using the output compare B register to give you the time when the output pin toggles. And the same with the fast PWM. You use the output compare register A to set the maximum value that the timer counter reaches before it goes back to 0. And then you use the output compare register B to get the actual PWM signal. And again, in this case, you're only going to have 1 PW output instead of 2. Here we are in the Atmel data sheet for the ATmega328, the microcontroller we're playing with here. And this is timer counter control register A. And these 6 bits that are marked here with letters are the bits that you're going to have to affect to get it to do what you want it to do, or to get the timer counter to do what you want it to do. And so these 2 bits here, WGM 01 and 00, they are part of the 3 bits required to give it to set the particular mode of your timer counter. And down here there's a table. This table here describes the 7 different modes of the timer counter. And I talked about the first 4 here: normal, phase correct PWM, and fast PWM. And then mode 4 and mode 6 aren't available. And then these are the 2 additional modes: PWM, phase correct, fast PWM. And this just describes the different modes of the registers. So I talked about top, which is the maximum value the timer counter will reach before it resets to 0 or starts going down, depending on what mode you've selected. And the timer overflow flag, which is one of the flags that can generate an interrupt. And that's, depending on what mode you're in, it gets set at different times. And so these 2 bits are in timer counter 0 control register A. These 2 bits are in register A, and there's a control register B, and it has the 3rd bit here. Probably don't need to use these 2 additional modes for most cases. You probably want to have the maximum resolution of your PWM, and so you only really need to worry about is these 2 bits here, and not worry about setting this one. And upon a power on reset or a reset, these register bits are always set to 0. So when you set up the microcontroller and the timer counter in the microcontroller, you don't have to adjust this bit here. It's already going to be 0 for you. It's just these 2 bits that you need to set. So that's how you set the mode. And these 2 sets of bits, COM0B and COM0A, set up the mode of operation of the I/O pin associated with the compare match register A or B. And there are 4 modes for each of the 2 pins. These 2 work the same way, so I'll only describe for COM-A. And depends on what type of mode you've selected for the timer counter, what that I/O pin actually does. And then I remind you that in order to get that I/O pin to actually work, you have to set it as an output. If it's set up as an input, which is the normal reset state, it'll come up in as an input. You won't get anything out of there. There won't be any PWM signal coming out of that pin. Now, so there's 4 different modes. Normal mode is what you'd use if you're not using a PWM output pin, and you just set these registers to 0. And again, on reset, they're 0 already, so you don't have to do anything with them if you're not going to use that I/O pin. And in this mode 1 here, the I/O pin simply changes state every time there's a compare match. If you're in a non-PWM mode. You know, I'm not even going to bother to go through all this, because in a non-PWM mode you're not going to use that I/O pin anyway. So let's just look at the I/O pin when we're in a PWM mode here. And again, if you don't well, obviously if you're doing PWM you want to use an I/O pin, so this is a state that you don't want it to be in. You're going to have to change these bits here to get it to do something, because this state here means that that output pin is disconnected and it's not going to give you a PWM signal. So in the first state here, or first mode here, if you're got your timer counter in the normal operation, what I described earlier, mode 0, the output pin is disconnected anyways because you're not going to use it. And then mode 1, which is too far down to go to that, get to that table. Mode 1 is the where are my notes here? Phase correct PWM mode. And so the I/O pin simply changes state every time the compare register matches the timer counter value. Probably a state that you don't want to use as well. And so these are the 2 states, or the 2 modes of this pin that you want to use, a 1-0 and a 1-1. And what I showed you in my little pencil sketch, this was the mode that would have been selected to get that form of the PWM signal. And if you want to invert the signal, you'd use this one. And again, for the see, that was fast PWM. For the phase correct PWM, it's actually the same. So it doesn't matter which PWM mode you've selected, these bits would be selected, set up the same way to give you the signal that you want. And then these are for the B pins, exactly the same. So that's how you set up the first part of setting up the control registers. Let's go and look at timer counter control register B. And now here's the third bit of the timer counter mode selection. And like I said, for most intents and purposes, this one would be 0. You don't need to go into the other two extra modes for the PWM, so I would just leave it at 0. These two pins here, or these two bits here, if you want to read through what they're for, you can read the data sheet for yourself. So I'm not going to talk about it here. So we're not going to bother with these, and they're going to be remaining at 0. And the initial value is what it is at reset. So if you just reset the microcontroller when you power it up or whatever, these bits are already going to be set to 0, and nothing's going to happen with this force output compare. So I'm just going to not talk about these ones right now. For this timer counter control register B, the important bits that we need to set are these ones here, which I talked about briefly in my previous video, which selected the clock source for the timer counter. And there are 8 different modes for this. So if they're all 0, there's no clock source selected, and the timer counter is not going to run. And then there's prescalers. Here there's 5 different taps that you can select from the prescaler. And remember that in this case the frequency source for the counter, for the clock for the counter, is coming from the main oscillator of the microcontroller. For an Arduino board, that will be 16 megahertz. In other modes, if you're just using the internal oscillator, that would be 8 megahertz. And then if you've got a board that you've made yourself, whatever the crystal frequency is that you've hooked up to it will be the frequency. And then, as I described in my previous video, this is a divide by 8. Divide that frequency by 8 by 64, 256, or 1024. And so you can slow down that clock signal to the timer counter. In PWM mode, I personally like to have the PWM running as fast as possible, so I would have no pre-scaling at all and just run it at the maximum. And so the period would be the maximum oscillator frequency divided by 256, which is the maximum count of the timer counter register. And that's how fast it would be running. If you're going to clock it from an external pin, have an external oscillator, or a different mode altogether for this timer counter, to use it as a counter. Again, I went through this briefly in my previous video, but I'll just talk about it for a moment. If you just want to make this thing a counter, just to count events that occur externally to the microcontroller, then you would select one of these two modes here and have the event pulse coming through an I/O pin, which is the T0 pin on the microcontroller, and that will increment, or well, it will just increment the timer counter register. So that's a very brief description again, or a review of how to set up the registers, the control registers in the microcontroller in order to get it to do what you want. So in this case, for PWM, I'm just going to set it to this mode here, 001, which I think I did. No, I didn't do it. I think I used this mode in the previous video because I really needed to slow down the counting of the timer counter so that I get a reasonable delay out of it. So the next thing we'll look at is the code, some software. So here we are in Atmel Studio, and I'll just quickly show you once more how to set up a new project in Atmel Studio. You click on File, New Project, and it brings this up, and we're going to be doing a GCC C executable project. Click on that. We'll give it a name, and in this case I think I'll do the fast PWM, so I'll call it fast PWM, a new project, and I have to browse into the directory where I want it. And and click on Create Directory for solution and click on OK. And now I've got to select my microcontroller, which is an ATmega 328. Where are we? 328, not P version. And now it's generating all the files necessary, including the first file, main.c, and I'm going to change the name of it. So I just go to highlight it with the right, and then right click with the mouse, go to rename, and I'm going to call it fast PWM. And you notice how it even changed the name up in here as well. So this is the file that contains main, and again we're just going to do everything within this file. So I'm going to shut down for now and do some typing, and then we'll go back and look at what I've done. Now, in order to figure out which pin we're going to use, I'm going to have to go and look at the I/O pins here. So bring up the table of contents, scroll up to pin configuration. So this is the package, the 28-pin dual inline package, and we're looking for output compare 0A, which is this one here, which is PD6. Port D pin 6, and then we'll go to the Uno schematic and look up PD6. Let's zoom in here so we can see what we're doing. PD6 is Arduino pin 6. So that's what we need to look at. This is so I can figure out which connector I want to connect to. So it's pin 6. Alright. Back to the code. So here we are in the code that I just wrote. It's pretty similar to what I did in the previous video with a few extra things. Still needed to include the interrupt. And in the project properties, as I mentioned before, go down to symbols here. We have to define this FCPU symbol. You could do it at the beginning of the file as well, but I think it's a good habit to get into to define it globally here instead of in a particular file. It's easy enough to do that here. So you just click on this green button, add item, and then type it in, FCPU equals whatever the value is. Now I'm going to use timer counter 0 to generate the PWM, but in order to give a visual display on the oscilloscope that's meaningful, I had to slow down the change of the PWM, or the duty cycle of the PWM. So I used timer 2 and set it up as I did with timer 0 in the last video, and made it generate a 10 millisecond interrupt. And basically the code is exactly the same for timer 2 as timer 0 in the previous video, just changed the zeros to 2s everywhere. And what I did here in this case is I used actual defined constants for setting the bits. Again, you could just use this binary notation, but again, this guarantees accuracy and this does not, because you don't know exactly which bit you're setting. You could make a mistake in your counting, and this is more or less error prone. So I did it the same way for all of these. And in this case here, for calculating the value to give you the correct 10 millisecond delay, I actually put the formula in here instead of the number that I worked out. So the number 155 I worked out on my calculator, but as I've said before in my previous videos, I like to get the compiler to do the work for me. So I just wrote the formula in here, and the compiler would figure out the number 155, and it would produce the same number. Now I looked up which I/O pin to use, and I decided for fun here, because this timer 0 can produce 2 separate and independent PWM outputs, I decided to make them both go. And so they're on ports D6 and D5. And so you've got to make them both outputs, as I did before in the previous video, and then I output zeros to them just to guarantee that they're actually 0. They start off at a known value. They should normally be 0 anyways on reset, but I kind of get into the habit of doing this. Sometimes you might want to set the port for some reason to start off that way, and then you do it here. So we already talked about timer 2. Now let's go down to timer 0 to set up the PWMs. So again, we're setting up the bits, the WGM bits, to get mode 3, which is the fast PWM. And so the 2 bits are set to 1, and then both COM A and COM0A and COM0B have to be set up in order to get the proper functionality of the 2 I/O pins. And in this case it's mode what is it, mode 2, 0, 1, 2, yes, mode 2 for both of those. And so you just simply set the bit 1 of each of those 2 pairs of bits. In this case I want the timer counter clocked directly by FCPU, and I don't want it slowed down because I want the fastest PWM. If you need a slower PWM for whatever reason, of course you can use the prescalers and slow it down, but in this case I want it as fast as possible. And now here I just preset the output compare registers A and B. I'm going to make one of them increase in PWM and the other one to decrease in PWM. And again, we have to set the interrupts here. Now we set up in our while loop here. And what we're doing in our while loop is just checking the 10 millisecond flag, which I defined up here. Oh, I forgot to tell you about a couple of defines up here. PWM change time, so it's 50 milliseconds between each, 500 milliseconds between each change of the PWM duty cycle. Just gives a nice visual display. And I need to count that, so I just created another variable here, PWM delay. And then here's my flag for set every time the 10 milliseconds is up. Again, since I'm using timer 2 instead of timer 0 to give me the 10 millisecond interrupt, I just change the name here to timer 2 instead of timer 0. Same idea, same interrupt service routine. Let's keep going down here. Let's go back to where we interrupted from. The 10 millisecond flag, it gets set. So what's happening here, most of the time this is just humming here, checking for this flag, and the flag is normally 0. So it's going to spend most of its time just wasting time checking this flag. I mean, it could do something else, or I could just use a 500 millisecond delay and do all this stuff with the 500 millisecond delay milliseconds, what I showed you before. But it's good to get into a habit to use this kind of method of timing your loops so that you can do something else. So when the flag is set, the first thing we do is clear it so we don't make the mistake of always leaving it set and then you just sit in this loop the whole time. Now we got to count the 10 milliseconds delays, so we pre-decrement the PWM delay, and if the result of the pre-decrement is 0, then we're going to first of all set it back to the delay time of 50, and then we're going to increment output compare register A and decrement output compare register B, and that will cause the duty cycle of the 2 PWM signals to change every 500 milliseconds. So that's about all there is to this code. It's again pretty simple. It will be available on my GitHub site when I'm finished with the video, uploading the video, so you'll be able to download it for free and look at it in more detail than I just went through here, and modify it to your own needs. Now let's look at the signals on the oscilloscope. So here is the scope showing the 2 PWM signals. They're plugged into Arduino pins 6 and 5. Those happen to be the 2 output compare pins for timer 0. And you can see that the duty cycle is gradually changing here. So this is output compare A and this is output compare B. So if you look starting at the trigger point here, you can see how the duty cycle in this one is increasing. Starts at 0 and then it's increasing, getting bigger and bigger, and eventually it reaches maximum duty cycle where the line is high. And we'll see here in a moment when this almost goes away and it's high for a moment and then it switches over. And we'll look at the other one, which I had a decreasing duty cycle, so you can see how this high point is getting smaller and smaller. If I were to hook these up to 2 LEDs, then you will see the 2 LEDs changing in intensity. So that's what the varying fast PWM signals look like. And Let's hook up a couple of LEDs and then we can see them dimming. So I hooked up a couple of LEDs to the PWM outputs. Arduino pin 6 and 5 are what they are. And you can see how they're, one of them sort of gradually getting brighter and then dropping off to 0, and the other one is gradually getting darker and then going back on to full intensity. So that's what the two different PWM outputs would be doing. I could show you how to use the phase correct PWM, but it's just going to produce the same results, and it's just a simple change in one line in the code. So I'm not going to bother to do that. I'll just include that in my code that you can download from the GitHub site. So that's about it for how to program timer 0 for PWM. The other two timers work the same way. Timer 1 is a bit more complex. There's a few more modes to it. Maybe in a later video I'll go into more detail on that one as well. Timer 2, which I'm using for the 10 millisecond delay, functions the same way as timer 1 in terms of how you set it up for the PWM as well. It works just the same. So I hope you enjoyed the video, and stay tuned for the next one. Thanks for watching.